Welcome to Ask and Learn.
So here we're asked to find the equilibrium constant. So we remember that we can relate the equilibrium constant and the cell potential of a reaction through the free energy. And this essentially by rearranging and exponentiating, we can find that the equilibrium constant is equivalent to this quantity, where the Faraday constant and essentially our gas constant are known. So essentially we have to know the temperature, which is given as 298 Kelvin. And now we have to know the number of moles of electrons transferred, etc. So we're given an unbalanced skeletal equation in this case. And we're asked, first of all, we have to balance this equation. And first of all, let's write out the oxidation and reduction processes in this case. So this is our oxidation reaction, while this here is our reduction reaction. And we basically need the number of moles of electrons on both sides to cancel out. So we see that basically we need 2 moles of electrons, so we have to multiply this by a factor of 2. For basically iron. And essentially in the end, we have 2 moles of electrons transferred. And we can essentially find our reduction potentials from a standard table. And we can find that the E naught of oxidation from our reduction potential table is 0.13 volts. And we also can find essentially the reduction potential for iron from Fe3 plus to Fe2 plus is equivalent to 0.77 volts, while the E naught cell would be the sum of the two since it's independent of the number, E naught is independent of the number of moles of electrons transferred, and this becomes 0.90 volts here. So now we can basically use the information we have to find the equilibrium constant, where we have 2 times 96.485 times our E naught cell over our gas constant times 298. And thereby we can find that our equilibrium constant is 2.77 times 10 to the 30. And this is our final answer.